So now to talk about everything else you need to know about elasticity. So just a bit of terminology, because there can be a fair bit of terminology thrown around here. I just want to say it's all the same terminology, it just looks complicated. It's a lot simpler than it looks like. So normally you're going to see something in the book like the blank elasticity of blank. Now what can go in those blanks? So in that first blank, it's normally going to be price elasticity. And that's what we're talking about here, right? We're talking about the response of quantity to price. That's why these curves are flat or steep. But you could put something else in there in that first curve. You could put income. In that case, you'd be saying, how does quantity demanded change when income changes? Right? That's like a question about, well, if people get wealthier, what do they do with their money? That's the sort of questions you might use income elasticity, say, for demand. What about income elasticity of supply? Is that mentioned in the book anywhere? No. Why not? Well, because we don't normally imagine that suppliers have an income that matters. People who buy stuff worry about their income. Can I afford this new house? Can I buy that Maserati? People who are selling stuff, they were thinking about corporations and things like that. They're worried about price and costs. They're not thinking about income. So we don't typically think about the income of suppliers. Doesn't matter. You won't see it in the book. So you'll see all sorts of terms like the income elasticity of demand. Like I said, that might be, you might look at, say, how much people spend on housing as their, and we'll talk about that at the end, how much people spend on housing as their income rises. You could talk about the cross-price elasticity of demand. And here by cross-price instead of price, what the meaning is, what if there's a change in price, but it's not of this good, it's of a different good. So there was a discussion there about, say, what if electricity prices go up? What might happen? Well, we might say, well, the demand for electricity falls. What would happen to the demand for swimming pools? That's like a cross-price elasticity. Because you're not saying, what does the price of swimming pools have on the demand for swimming pools? You're asking, what's the effect of a change in electricity prices on the demand for swimming pools? Right, so that's when you tend to have questions about cross-price elasticity. Okay. So what we want to do, and what elasticity is all about, is calculating a number. So most of you guys will get quite confused when we go into the calculations. So I'm just trying to put the calculations at the end rather than the beginning, so we can lead into this gently. So we want to calculate a number to attach to a curve. And basically, we want to calculate a number to attach to the curve to tell us whether that curve is steep or flat. So any of you who remember, say, 9th grade algebra should go, oh, wait, well, we spent half of 9th grade algebra calculating something that tells us whether a straight line is steep or flat. It was called a slope. You remember y equals mx plus b? We still teach that in 9th grade algebra. Anyway, the m is called the slope. It's a change in the p, in this case. The slope of the line would be the change in p divided by the change in q. That's telling us by how much does p change if we vary q by a little bit if we're going along this line here. So you might think, okay, well then look, if we're looking at changes in p's and changes in q's, and we're wondering about whether this line is steep or flat, why don't we just use a slope and be done with it? Why on earth do we need to go a step further and introduce this new thing called elasticity? Why did I waste all that time in year 9 calculating slopes? Okay. The problem is you can't really use slope here. And the major reason is this second paragraph here on the left. When you measure slope, you're saying that, you know, if the quantity rises by 20 kilograms, then the price falls by 5 cents. So when you're talking about slopes, you're always thinking of the units. There you're thinking kilograms and cents. So that's going to tell you something about the slope if it's measured in kilograms and cents. The problem is if you measure it in kilograms and dollars, you're going to get a different number. If you measure it in dollars and grams, you get a different number again. If you measure it in cents per ton, you'll get a different answer. Your slope depends upon what you're measuring the horizontal and vertical axes in. So that means I can get any number I want to if I just simply play around with what I'm measuring in Q and P. The slope will change. That's a problem because we want to be able to talk about steep and flat and not have to worry about what the hell we're measuring any of these curves in, what the particular units are. So that's the reason why elasticity is always presented as a number like 0.2 or 0.5 or 1.8 or 2.3, but you never see any cents per kilo or kilo per cent or cents per ton or dollars per blah. There's no units on elasticity. And the reason is that elasticity is what's called a unitless number. It has no units. It's not measured in feet or meters or pounds or cents or waffles or anything. It's just a number, 0.2, 1.5. You don't have to put a unit after it. Okay. And that's how you get around the problem of what if we measure stuff in units and slopes measured in units, and that's why we can't use slope. Because what on earth does a steep slope mean if we're measuring in terms of cents per kilogram? What do we do? Well, the thing to think about elasticity is measured in percentages. Right? So elasticity is a ratio of percents, basically. It's a ratio of a change in the percentage change in quantity divided by a percentage change in price. So percents are just measured in percents. There's no cents or kilograms or anything. You don't say handbags today are being sold for 25% less dollars. You say handbags are being sold for 25% less. You don't say there's 30% less grams of fat in these muesli bars. You say the level of fat is 30% less. You don't have to say grams or tons, whatever. So percents have no units like that. And since we divide 1% by another, the percents cancel out, and all we wind up with is a number 0.2. So that's a nice thing. It's desirable. It means it doesn't really matter what the context, how we're measuring things are. We'll wind up with a pure number, 0.5, and that's it. You don't have to say anything. Okay. Okay, I've said a couple of times why I hate textbooks. This is another reason why I hate textbooks. Because they all lie just a tiny, tiny, tiny little bit. Probably because if you tell the truth, it gets really, really complicated. The more the truth they tell, the more complicated things get, and so the more difficult they are. So it's a lot better just to lie a little bit and not worry about the complications, then kind of fiddle and sort of wave your hands a lot and say, don't worry about that stuff. You know, it doesn't really matter. And textbooks do that all the time. So here's a case in which, yeah, you are lying a little bit. The textbook does nicely mention it in one part and then proceeds to ignore it in every other part of the textbook explanation. The problem is, typically the lines that you draw, the curves that you draw in micro, are straight lines because it looks nicer in textbooks. And it looks nicer in PowerPoint. And, you know, my PowerPoint doesn't have a really nice drawing feature, so, you know, all of the lines I draw are straight. The problem is the elasticity is not constant along a straight line. So in fact, if I calculated the elasticity all the way along that demand curve, I'd get different numbers. Just because of the way that elasticity is calculated. The slope is the same along a straight line, if you remember back to your 9th grade algebra, but the elasticity is not. So we've traded off one problem for another. We've traded off the problem that we don't have to worry about what units we're measuring stuff in. But we've got the problem, actually, that elasticity is only right for a tiny little area. So within this circle, elasticity is approximately the same. Once you go outside that circle, you can get whatever level of elasticity you want to, depending where you measure this. So that's what you have to accept. That elasticity is not a statement about the whole line. It's just telling you something around where we are right now. So typically what we do is we say, well, here's the market equilibrium. And around this market equilibrium, the supply curve is relatively flat. That's all it says. And in most cases, economics, that's fine, because all we're thinking about are small changes. You know, the carbon tax comes in, 23 dollars per ton of CO2, whatever level we're going to choose. That's going to have 1%, 2% increase in electricity prices. It's tiny. It's going to have maybe a 1.5% increase, a decrease, in household real purchasing power. Small. Most changes that happen in economics are tiny, and that's what we're arguing about. We're arguing about relatively tiny changes. And because of that, we're almost always inside this circle. So even though we're going to say, look, elasticity, it's, once you leave the circle, elasticity could be anything. In most situations we'll be thinking about in economics, we will only be thinking about small changes, marginal change. And so in that case, it's fine. We're going to say elasticity is 0.2, kind of around that net circle. So we're going to say if price changes by so-and-so, we'll always use an elasticity of 0.2. We'll assume it doesn't change. As long as the price changes aren't too much, that's valid. If you're thinking about really large changes in things, then no, the elasticity will change. So you might want to have to maybe use something else. About what sort of tools you use to solve these problems. But elasticity is fine for just marginal changes because it's going to be relatively around 0.2 as long as you stay relatively close to where you calculated elasticity in the first place. The book does draw nicely some constant elasticity demand curves, and they're curved like this. The book draws what it calls a unitary elastic demand curve, and that's kind of a fiddly curved line like this that mathematicians call something close to a hyperbole, and it's certainly not a flat line like this. So flat lines have changing elasticity all the way along. So it's a little bit of a lie.